Geometry's like everywhere, right? I
Oh,
mean, when you think about it.
it really is.
The symmetry of a leaf. How about the arc on that bridge?
Yeah.
Even how our furniture's, fitting together.
Hmm.
And like at the heart of it all, it's quadrilaterals.
Definitely.
So we're going to be diving into chapter 8 of your textbook, which you might remember as not exactly like, the most exciting thing from school.
Right.
But
Yeah, not a pastry.
I think we're going to uncover some intrigue with these four-sided figures. What do you think?
Oh, absolutely. And I think what we often overlook is that quadrilaterals, they're not just like these abstract concepts.
Hmm.
They really are the building blocks of so much in our world. And that's because of all these unique properties.
Okay, so to ground this deep dive, let's just real quick acknowledge that the source material that we're looking at focuses on convex quadrilaterals.
Okay.
And you can kind of think of this like those connect the dots puzzles we all did as kids.
Yeah.
As long as your lines are staying inside the shape,
Yeah.
you are in convex territory.
You got it. Exactly.
Yeah.
And within that territory, like you start to see this fascinating interplay between, the angles, the sides, and then those diagonals. And
Right.
and did you know that a seemingly simple fact, I mean, we all kind of know it, that the sum of the angles in any quadrilateral is always going to be 360 degrees. That underpins like some really complex architectural and engineering feats.
Wow, that makes me want to look twice at all the buildings we see, huh?
Exactly.
Okay, so before we go too far,
Yeah.
let's just do a quick rundown of the types of quadrilaterals that our listeners going to find in here.
Okay.
We've got the classics, right? We've got parallelograms,
Yes.
rectangles, squares,
Mm-hmm.
but then we've also got the, maybe a little more specialized trapezoids, rhombuses, and then everybody's favorite kites.
Right. And, it's that specialization, those unique properties that make each type so interesting.
Okay.
For example, when you think about a parallelogram, right, and those parallel sides, that's not just a definition. That's actually the key to understanding why certain shapes are able to tessellate, or in other words, like tile so efficiently.
Interesting.
Think about a honeycomb.
Okay.
Right. It's a perfect example of how nature will actually optimize for strength, but using like the least amount of material possible.
It's funny. I never really put those two together, the honeycomb and the parallelogram.
Yeah.
But it makes sense. Nature optimizing like that.
Exactly. Exactly. And it's not just honeycombs either, right?
Oh, yeah.
Think about, how about bricks?
Yeah.
When we lay bricks to make a wall that's nice and stable,
Right.
or even just like how floor tiles can all fit together without having those weird gaps.
Yeah.
It all goes back to how parallelograms work,
Yeah.
Especially the fact that their opposite sides have to be, they're equal and they're parallel.
So that's what gives them the superpower to tessellate.
It is. That's the key right there.
Okay, and speaking of parallelograms, I thought it was really interesting how the source material mentioned burfi,
Oh, yeah.
these Indian sweets that are cut into parallelograms. What's the deal with that?
Oh, the Burfi thing. Yeah, that's a really cool example of how, geometry is being used in the real world that we probably don't even notice all the time.
Right.
Shopkeepers, they've been doing this forever, probably without even realizing it. They're using parallelograms to carry, the most amount of burfi.
Okay, so I'm picturing all this delicious burfi,
Yeah.
but help me with the geometry here. Why would you use a parallelogram over, let's say, a rectangle?
All right, so imagine, you're trying to fit as many of the same shape as you can onto this tray,
Okay.
right? But you don't want to waste any space, right?
Right.
So you could use rectangles, that seems to make sense, but then you're often left with all these gaps, especially when there's not a lot of room.
Yeah, like when you're trying to fit those last squares of baking chocolate into the pan, and it never really works.
Exactly. That's a great example. But with parallelograms, because the sides are slanted, you can usually fit them together way better.
Okay.
And that means less wasted space, right? Which means more burfi on that tray.
More burfi.
Huh.
I love it. Okay, so it's like this sneaky little geometric trick to get the most out of your tray.
It really is. It works better.
Okay, so next time I'm in the sweet shop, I'll be looking at the burfi for sure. I'll be checking out their geometry.
And I know what you see.
I will. But, we're talking about efficiency and all these interesting connections.
Yeah.
And then there's this theorem in here, the midpoint theorem. It's just why is this in here? Because it's about triangles, right?
Right. Yeah, it does seem like a bit of a detour.
Yeah, so how does it fit in with what we're doing with quadrilaterals?
That's a great question. And honestly, at first glance, it really does seem totally unrelated.
Right.
But just stick with me for a second.
Right.
Because the midpoint theorem, even though it's about triangles, it helps us understand parallel lines, which are like the heart of quadrilaterals, right?
Okay, you're making me curious. So remind me, what's the midpoint theorem again?
Okay, so basically, if you connect the midpoints of two sides of any triangle,
Yeah.
the line segment that you just made will always be parallel to the third side of that triangle, and it's going to be half the length.
Okay, I'm picturing it. All right, so we've got this line segment that's like magically parallel to that side.
Exactly.
But how does this relate to quadrilaterals?
Okay, well, remember those diagonals and quadrilaterals?
Yeah.
They make triangles, right?
Oh, okay.
So now, imagine you've got these parallel lines,
Okay.
and they're being intersected by these other lines. We call them transversals. They kind of cut across the parallel lines.
Okay. Yeah,
And the midpoint theorem, if we use it in the right way, it can actually help us prove some cool stuff about these segments that are, being cut off on those parallel lines.
Okay, so even though we don't see triangles like directly in that situation,
Yeah,
the midpoint theorem is still working in the background.
exactly. It's like it's working behind the scenes, and it's all based on those principles that we talked about.
That's so interesting.
It is. It gets even cooler when we start looking at specific types of quadrilaterals, like when we get to parallelograms,
Oh, okay.
and we see how those special properties mix with the whole parallel lines and transversals thing. But I think we should save those geometric gems for the last part of our deep dive.
It really is amazing how, like, the midpoint theorem, which seems, I don't know, kind of simple when you first hear it,
Right.
can, like, have all these other effects on, more complicated geometry stuff.
Yeah. It's like this little key that unlocks these hidden patterns.
Yeah.
And it just goes to show how elegant geometry is, Everything's connected.
Totally.
And when we understand these, like, basic, almost like foundational theorems, we can really appreciate what we see in the world so much more.
It's true. Okay, so we've been talking about these, like, special geometric gems about specific quadrilateral.
Oh, yeah, we can't forget about those.
We can't leave our listeners hanging.
Definitely not.
So we've talked about parallelograms. But what about, like, their cousins,
Yeah.
like the rectangles and the squares? What makes them so special when it comes to all this parallel lines and transversals business?
Okay, well, let's think about rectangles for a second.
Okay.
Remember how we said that diagonals in a parallelogram, they always cut each other in half?
Right. They bisect each other.
Exactly. Rectangles, they take that idea and they're like, we're going to take it one step further.
Oh, okay.
It's not enough for the diagonals to just bisect each other.
Right.
Those diagonals also have to be the same length.
Oh, okay.
Yeah, think about it. Those perfect 90-degree angles in a rectangle.
Right.
They're forcing the diagonals into this, like, perfectly balanced.
So it's not even just that they're cut in half, but, like, both halves are identical?
Have to be, yeah. They're like twins.
Oh, that's so interesting. Okay, so does that actually matter for anything, like, in the real world?
Oh, absolutely. This is super important when it comes to building stuff,
Oh, okay.
To make sure that whatever they're building is actually a rectangle. What do? They measure the diagonals.
Oh, that's so smart.
And if the diagonals are the same, then they know that those corners are actually 90 degrees, and then everything's stable.
Right. You don't want wonky walls.
Exactly. No wonky walls.
Okay, that makes a lot of sense, actually.
Yeah, and, speaking of wonky, what about squares?
Oh, yeah. Okay, so squares are like the overachievers.
They really are. They're like, we're going to take it to the next level.
Exactly. So what about their diagonals? What's going on there?
Okay, well, remember, they're inheriting all that good stuff from rectangles, right? So the diagonals are equal. They bisect each other, but squares have their own little twist.
What's that?
The diagonals in a square, they're not just equal. They also bisect each other at 90 degrees.
What? Okay, so they're perpendicular too.
Perpendicular, yep. They meet right in the middle, perfect 90-degree angle. And that creates, get this, 4 identical right triangles.
Oh, wow. So much symmetry going on in there.
So much symmetry. It's like squares just hiding 4 triangles inside.
Right, it's like a disguise.
It's a great disguise, I have to say.
It makes you wonder what other, like, secret relationships and stuff are hidden when we start thinking about the world this way, like geometrically.
That's what I love about it.
It's true.
Every time we dig a little deeper into these shapes, it's like, oh, there's a whole other layer.
Yeah. We've gone from, like, the basic definitions
Right, we started at the beginning.
to, like, honeycombs.
Honeycombs, don't forget the Burfee.
Oh, yeah, the Burfee.
2 buildings. And it's all connected to quadrilaterals.
Who knew? Right.
I mean, honestly, they're just way more interesting than they seem.
It's true. There's definitely more to these shapes than meets the eye.
I agree.
Well, thank you so much for guiding us through this deep dive. I really enjoyed it.
Oh, the pleasure was all mine, honestly.
This was great. And to our listeners, we'll see you next time.